So if we'll consider our discussion on forces, and a force being a push or a pull on an object. And then we have to ask ourselves, why is it that we're applying a force to an object? And that force is being applied to an object in order for us to change its motion. So we're talking about acceleration, which includes speeding up, slowing down, and turning. So forces cause the accelerations to happen. So without acceleration, there is no force. Without force, there is no acceleration. The two are hand in hand. So when we consider a system that we're looking at, what we first have to do is try to figure out what forces are acting on the object. And then we're trying to find out if the object is accelerating or if the object has constant velocity. And constant velocity situations are at rest or constant straight line velocity. So it's either one of those two. And when we look at acceleration, what we're looking for is that the net force will not be zero. When we're looking at constant velocity, the net force will be zero. So if we consider the system that we have in question, there's a puck resting on ice that is frictionless, and we want to draw the force diagram of the puck. First I have to identify the system. Now I know I have gravity and a normal. So I draw that. Force of gravity on the puck by the ice. And I draw a somewhat similar arrow. Force normal on the puck by the ice. I'm sorry, this should be by the earth. So in this case here, when I consider this case, and this is just a situation that I've applied to draw this. This could not, there could be a multitude of different situations. So what I have here is I have a downward force that is the same in size as the upward force, but they're opposite in direction. So when I look at these two, if I had plus 5, minus 5, then those two, if I added them up, would come out to be 0. So the sum of my forces would be 0. So then I come over here and I'm trying to pick which one of these two then is it. It is definitely the sum of forces is 0. Is it at rest or is it in constant straight line velocity? So that's what we're trying to answer. Upon further review, if I gave this block of, or this puck, a shove on ice, and there was no friction, and it was traveling at a constant velocity, then there would be nothing needed to keep it moving. So if I were to draw at rest, and constant velocity, it would look the same. Constant velocity can have arrows in the x direction if there is friction present. If we are frictionless and we are at constant straight line velocity, then there are no other net forces acting on the object. So this idea of net force 0 is called equilibrium. At rest, and this would be a balanced forces. And at rest would be static. And constant straight line velocity would be dynamic. So there are two different kinds of equilibrium that we're dealing with. If we look at the other side of the coin, we have constant velocity. If we look at the changing velocity, we simply call that, when we have a net force that is not equal to zero, we just simply say that we have a net force. And that would be unbalanced forces that are being applied. So if we're recapping what we have here, is that the reason we draw force diagrams is we're trying to explain either a change in velocity, which would be an acceleration, or we're trying to show a constant velocity, no change in motion. So first thing we have to do is figure out, is it net force or is it equilibrium? Then when we dive into it deeper, we would know this. The only way to tell the difference between these two is if we told you initially that it was moving. So if I said the velocity was zero, then that would be static. If I told you that the velocity was not zero, then it would be dynamic moving. And this, of course, also depends on us knowing what the velocity is to determine what the object is doing. I can't identify that it is accelerating without knowing what the velocity is doing, but I cannot tell what kind of acceleration it has without looking for the velocity. And we'll look at some of those examples here in just a minute. Let's go ahead and stop that.